We got 610 number 9. 610 number 9 is essentially the problem I had outlined in the static equilibrium lecture video, episode 9 or 8, I think, where I've got a stick here. It's being supported by a cable at an angle that's attached to the wall. And the only thing fixing the stick to the wall here is friction, right? There's no hinge, there's no axle, there's no nothing. We're just relying on friction to hold it in place there. And the way I proposed it in the lecture was it would be asked either one or two ways. Either we would put the hanging weight at some position X and determine what coefficient of friction would be needed to hold it up, or vice versa. We would know the coefficient of friction and figure out how far out or how far close to the wall X we could put the hanging weight. So in this case, they've given us the coefficient of friction and they want us to figure out, hey, where can we put that hanging weight so this thing doesn't fall off the wall and it stays in equilibrium. So first step, right, draw a free body diagram with the forces at the points of the application. First thing, I always write my torque equation first because usually that's a good place to start. It eliminates variables, makes the math a little bit easier. So picking my axis of rotation to be the point of contact with the wall, I got my normal force here and my static frictional force here. So I don't know either of those. If I knew the normal force, I could figure out the static friction because mu normal. We are maxing that out, so we do get to put in mu static normal for this static frictional force. So I got two unknowns there, so I'm going to pick my axis of rotation to be there, and that will leave me only the tension force is an unknown force. Unfortunately, it also leaves X as an unknown in my torque equation. So I'm going to have to go a little bit more and then come back to my torque equation to finish the problem off. So setting up my torque equation, I got a positive torque here. I'm calling clockwise the positive direction here. The stick's trying to rotate down. So we've got the weight of itself. We got M2G acting at L over 2. That's applying a positive torque, making it rotate down. We've also got the torque from the hanging weight, M1G, and it's acting at X. So we've got another positive torque there, M1GX. And then we've got the cable holding it up, keeping it from rotating clockwise, causing a counterclockwise rotation, or trying to. So we got that in as a negative torque. Again, we got to do a cross product here because they aren't perpendicular. So our lever arm of L times then sine theta times tension, just to use our cross product, right? Using that Y component there. All right. But unfortunately, I can't solve for X without the tension. So if my end goal is to figure out X, I got to have tension first, which means I got to look at my sum of forces. So let's look at my sum of forces in both directions. In the horizontal direction, I got T cosine theta minus the normal force. That's going to be equal 0. So we have a nice easy relationship between tension and normal. Tension is just normal divided by that cosine to get into component form. So we got our relationship between tension and normal. So if I knew the normal force, I could find tension. If I had tension, I could find X. So last thing we can do is write down our sum of forces in the Y. We got our static frictional force acting up, holding it up. We also have the vertical component of the tension, T sine theta, acting up, positive, and then the two weights acting down, negative, both negative, and then those all got to add up to 0. So it seems like if we have 4 unknowns, we need a fourth equation. Our fourth equation comes from just substituting in static friction and mu normal. So we had 4 unknowns, we got 4 equations. So we have mu normal for our static friction. I'm going to throw in tension there, which is normal over cos theta, so that everything now has normal force. I only got 1 unknown. I can figure out my normal force, a little bit of algebra, weight forces on top divided by mu plus tan theta. That gives me my normal force. This is a number problem, so then you just go back and work your numbers. Once you have normal force here, you can get tension easily, and then once you've got tension, you can get X. All right. That's a good one. This is pretty straightforward, but it kind of brings all that static equilibrium things together, which is why I chose it as one of my original examples. So there's the math for it.